you, babe. If it ain't love, why does it feel so good? Why does it feel so good?
我们请到了，我今天给大家介绍一下，我们请到了格鲁吉亚，他是工业大学的教授，他是呢格鲁吉亚自然科学院的院长，他是叫欧洲地中海科学院的院长，所以呢又是俄罗斯和格鲁吉亚的院士。So it's our honor to invite Professor Paata, who is from Georgian Technology University, and also the president of Georgian Academy of Natural Sciences, and also the president of Europe Mediterranean Academy of Art and Sciences, right?
Yeah.
So it's very high level and academic. So could you with warm applause welcome the Professor Wells lectures. Okay.
I have a time, yeah? Mr. Chairman. Yeah. Thank you. First of all, I am very glad to see you here, and so nice young people, my colleagues. Professor, when he introduced me, he's saying that I'm working in Georgia now, and Technological University and at the same time the State University. I'm physicist and mathematician. I am not a chemist or biologist, but our task in this time, in 21st century, is to use what we did in physics, what we prepared for healthcare, for medical application, for biology, for new science, which will develop the health, and we will come to the age 200 years old, or something like that, yeah? Sometime we will achieve this level. So, what I would like to say now, first of all, I was professor in Harvard University, US, Berkeley in California, and now I'm professor in the University of Paris in Sorbonne, of course in my discipline, in physics, technology, and biophysics also. And I'm looking to you, and you are not I think that you are better, not equal, and you have possibilities to achieve the main goals and be the, I think, that the leading scientist in your field. But what do you need for this to understand my discipline? Physics. Physics is a nature. Greek word means nature. So what we are doing, we are trying to understand what's happening in the nature, and later on to use it and to manage. Yes.
Do you use a pointer? Yes.
Yeah, thank you. Check.
It works.
Yes.
It works or not?
Yes, yes.
You should turn on the okay, we say. Is turn on? Yeah?
Yeah,
Okay,
okay.
up, down, down.
Okay.
Okay.
Very well. So, and now I will speak about very concrete things, yeah? And I will try to, if time will help us to do this, I will speak about some subjects. First subject is, as I told you, how to use the knowledge, new knowledge in physics, technology, for medical applications, for biological applications. And my first talk is about the hyperthermia. Do you know what is a hyperthermia? Hyperthermia is a process when you try to treat by temperature the disease cells in order to treat the cancer. it's common. We are not inventing this. It's common, and it's about 15 years old direction. But what we did, our group, our international group, and one lady is here, you can see. This is how to prepare the nanosystems which is possible to use as a main engine to make treatment of disease cells by process of hyperthermia. The next slide, how we can show me. No.
Okay, it works.
No, yeah, it's right.
Okay.
Yeah. Thank you. So, I think you understand in English, or after I will answer the questions. And I will tell you very quick what is necessary. The necessary is to achieve the temperature surrounding the disease cell about, here is, we wrote 42, 44 degrees centigrade. You know why? Because higher is good, but it's impossible. It is damage our body system. So we need to have this temperature. Sorry. And I will go. And what is the problem? Problem is if we are using the particles, we are using the different particles, metal particles, it's problematic to have exactly the temperature we need. No? And what is the temperature is making? Do you understand, yeah? Temperature, yes sir, these materials are situated, surrounded the cell, any cell, diseased or, I mean the good cells and so on. And it's treated. If it's a normal cell, nothing happened, yeah? But if it's the disease cell, it's starting to kill the genetic source of disease. You know, we are making now theory how it's happening, but it's in practice, this is possible, and we are doing it. Not we, I mean me, myself, our scientists and all the world, yeah? Mainly this process we used together with our German partners nearby Hanover in Germany, in clinics now, and it works. It works. So we try to make the theory, but in practice it is very needed, you know, for the patients now, and because of cancer is a very common disease now and very dangerous disease, most of them. So this is a very simple thing, yeah, to make the injection. I will go the main things. What we need. We need to prepare magnetic nanoparticles. So why I'm telling you? So in our team we have biologists, chemists, physicists, metallurgists. Why? Because it's necessary to know those all disciplines. It's impossible for one person to know everything, and we use the knowledge for different people. Of course, we used of course also the medical doctors and specialists of biology. What is necessary? The magnetic nanoparticles need to satisfy, it's written here, the following criteria if they are not be safely used in humans. Be biocompatible, have a large area of hysteresis loop, have a low toxicity as it possible. And I will tell you, biocompatible is understandable for you. What does it mean? Yeah, don't damage the area when you are using. The large area of hysteresis loop is physics. You know, magnetic system, ferromagnetic materials have a hysteresis. You know, on the one direction is and one vector is another vector have some not the same track, you know, and in between them this is a domain, magnetic domains. Yeah, magnetic domains have a property to let's say to orient it in ordering by the magnetic field. You know, how we can achieve the temperature? You know, we inject these particles. I mean, suspension. We are making suspension first of all. It's very simple, yeah, and with physiological liquid and magnetic particles inside, yeah, magnetic power, including magnetic particles, and we injure this. No, we are inject this in the area. This is the area I don't like to show in my body. Yeah, nobody's body is. So, and what is happening later on? As I told you, these particles situated surrounded these cells, and when the patient are lying later on in MRA, in magnetic field, yeah, you should choose the temperature, time and temperature, and magnetic field influenced to the body on magnetic particles, you know, and you heat this area, yeah. In temperature you need 42 or 41 or 40 degrees centigrade, and these results are very, you know, the disease is very sensitive, and because of it the results are very visible. So, but our task was to prepare these particles with low toxicity. It's a problem, because what is magnetic materials, you know? This is cobalt, ferrum, nickel, manganese, and some others, but best is ferrum. I mean, in toxicity. Iron, I mean, yeah? In toxicity, but even iron have problems, yeah? Because of it, our task was how to diminish the influence of toxicity of, because the patients are the weak, yeah, and the immune system is not so strong. So we need to help them to adopt, and this, and because of it, we elaborate the quite new system. We are preparing the magnetic particle as a nano powder. For example, cobalt. For example, any of them, you know that you can measure first with ferromagnetic properties, yeah, and it should be very pure, of course, chemically pure and so on. It's not so difficult, yeah, using the, you know better than me, the chemical technology and so on. But we decided to put it encapsulated in carbon nanotubes. And we are doing this because carbon, I mean, yeah, carbon is not toxic at all. So in between the chemical elements is less toxic element we know up to now. Every elements are toxic, of course, but carbon is less. So we are using the carbon, and we are trying to, and I will shortly, and later on we may, this is how we measure later on, how is this is curves to show the temperature dependence it is a main part is so-called specific absorption rate. Yeah, how the temperature are depending to concentration of magnetic nanoparticles inside. So our concrete task was to prepare magnetic nanoparticles, less toxic and well situated and well and suitable for the body, for organism of the human. So, and we make the necessary measurement. This is the way we use nickel, cobalt, copper, so on. Any material which is possible to use as material which can activate the hyperthermia. So you know now what is hyperthermia. Hyperthermia is the process when one element or one material is responsible for starting the temperature increase. Yeah? And temperature increase should be done through, you know, not only magnetic things, but here by magnetic influence. So, which is very important because for this treatment, gamma rays are mostly using cobalt 60, yeah. And gamma rays is a very strong and unacceptably strong. Or even, for example, for treatment are using the gamma rays, and also for cobalt 60, which is very strong radiation, has influenced on the hair and everything. Or cesium-137 isotope also. It was known last 40 years as anti-cancer, elements, but they're influenced on, and we would like this direction in science technology for the biological medicine is how to use the most suitable temperature, which is not damage anything, and temperature is very, acceptable for the body, you know. Not so acceptable, temperature is also not, you should be in good range, yeah? Because, of course you can use 50 degrees, but he is damaged 50 degrees or more. You should be, the best solution is to use not more than 40. Yeah, because you need sometimes 2-3 hours for treatment process. 2-3 hours is strong for the body, yeah? Yeah, because you know, you don't never forget that you are doing this with patients which are weak because they have disease, yeah? They have problems. So, and now it's chemical works, what powder is better, 10 and 40 nanometer, 350 between these sizes. Why? It's technologically easy, firstly to prepare, and secondly to inject to the, with a solution, with a physiological solution, and it inject to body, to the place where the more concentration of disease cells. It's very different, you know. Everywhere you should have a disease cells. So it's a very busy process, yeah, very delicate process to inject. So you need even smaller is better, but smaller don't. Sometimes by small particles you cannot reach the temperature you need. Yeah, this is work. This is research work. How it's possible to prepare the best solution with best influence and best temperature results in smaller time, in low time. Not put the patient 6, 7, 10 hours under the magnetic field in an MRI system, for example, you know, magnetic MRA system. What does it mean? So this is how we prepare this, and this is what reaction when we are using the C, and that we need to have a big, not high, big hysteresis, which means that influence of magnetic field will be higher in this case. Yeah. Hysteresis loop. I think that you know physics because it's necessary to start to explain to you what is the magnetism. You know, I'll tell you, it's very interesting. For example, have I time, Sam? Yeah. For example, I would like to explain you something in physics. Yeah. You know that we have fields and particles in physics. Fields. For example, electrical field. And what is the main particle? Electron, yeah?
Electron.
We have the gravitation field. What's the main particle?
Gravitation.
We have a biological field, so-called, it's not existing. I will tell you if you will ask me later on, but it's a bioton. And we have the magnetic field, magneton. Unfortunately, or fortunately for you, because you will discover later on, we know only electron, what is it. We don't know what is a magneton. Influence of magnetism, we know, but how it's happening, we don't know still now. Do you understand what I mean, yeah? We know that it should be happen through the magnetic particle, which calls the magneton, but we didn't see what is a magneton, so because of it we manipulate with our knowledge how to, because we need this even for healthcare, for different applications. So we are doing this, and because of it we were trying to increase magnetic properties of the system in order to receive the reaction stronger, to have the strong reaction. This is our problem. So it's different. Why I'm trying to go quicker, because I would like to give you the information about another opportunity, also another presentation. So we measure this by electron microscopy. How it's possible, best solution is, of course, because it's easier to encapsulate it in the carbon nanotubes, as I told you. You know what is a carbon nanotube. I think that everything is, it is not a Fullerene. Fullerene is a more different form. It is a nanotube, simple nanotube, and you encapsulate it, spherical particles, some spherical particles in one nanotube, something like that. So, and this is a nanocomposite. Our nanocomposites is how they are situated, how they are in, I am using this. And this is X-ray diffraction spectrum of samples with, oh, I forgot. We tried to mix the compounds in between two different ferromagnetics. For example, nickel, copper, ferrum, nickel, something like that, in order to achieve the higher magnetic field. So it's a huge job, yeah, to use the different compounds in order to receive the different level of, higher level of magnetic field. So this is results of analysis and so on. And very interesting, as I told you, we need to find out now, my personal work now, during the last 10 years, I am like to find the resonance pairs. For example, when I speak with you, I would like to tell you what make your brain be in resonance. What means the resonance? If you are interested in strongly, you receive this information quicker, you know. So everywhere is a resonance. So we would like to find out the resonance peak for this concrete material and do this system to use the resonance. In this situation, we need less energy for MRA and so on, because when we are coming to resonance, we receive the best results, of course. And of course, we are trying to measure for our all systems, all compounds, the resonance curves. Are you following? Guys, girls, are you following me or not?
Yes,
This
yes.
is, if you don't understand something, tell me, it's better. So, now I told you, for example, this example is nanoparticles of iron in carbon matrix. So, carbon matrix is what we decided to do. You know, that's a good result in practice also. It is not only blah, blah, blah. It's medical results and biological results is also achieved. And carbon matrix is in this stage, of course, is the best solution. Later on, I don't know, maybe you will invent something more interesting. This is how it's possible to do. This is ferrum carbon composites. And this is why I do it. This is anti-oxide, disoxide systems, and so on. And this is my lab. My lab is laser. My lab is using everywhere the laser, optical lasers. Yeah, why? Because with lasers, what is laser? Laser you can manage the wavelength. And for example, as I told you, as a biologist, you are Professor Dan, yes? Is it? Yes. I would like to look to your eyes and try to read what you need to hear. So, yeah, and I will tell you this, what you need to hear, yeah? This is resonance, and we are using the lasers to measure through your eyes, yeah? What is best, how to say, reaction of you by laser. We will measure, and I will try, when I know that what you do like in wavelengths, I will send you the waves in this direction, not opposite or this line. Do you understand what I mean? And we are using this method in technology, in everywhere. Try to use this. So, and it's useful. Believe me, it's useful, very useful, as in life, as in biology. So, this is laser-generated magnetic nanoparticles. We are using the lasers everywhere. This is system how we are doing this. Different lasers, different methods, different technologies, but using the different wavelengths. I mean, red, blue, even the violet lasers also. You know that copper is a green one, for example. Copper lasers, green one. Neodymium are the infrared and red, but we use mostly for these concrete purposes. We are using the, the visible spectrum. Yeah. So visible colored laser. So this is after laser technology. This is our original system. We patented in the United States 2 times. It's an installation laser plasma technologies for different applications. This is our original work, very original, may I say. And also very interesting, but I don't know. It's some. Do you know if you know what is it? This is deep physics, the Mills-Bauer effect. It's a very deep physics, but we are using the so you know the feeds on last places of so-called Zeeman splitting, when electron is coming and in the fields these electrons are splitting 2 spins, and this is Mills-Bauer effect. These magnetic particles are very, very sensitive for this these effects of splitting, yeah? And because of it, this quantum effect, of course, and its results are higher, I mean. You understand, yes, we count on influence, I mean, delegates, so this influence is very important. So, this is how we prepare a Mös-Bauer spectrum laser generated. This is Mös-Bauer spectrum of laser generated systems, and
Take your time.
yeah, absolutely right. You know, this is what I'm telling to you. It is not a quite, I mean, it's some fantasy. Yeah, it's an everyday job. Everyday job. But we are looking what you do in the future. how you will develop this all. Okay, this is different pictures and so on, so on, so on. What we plan now to do, we're planning to analyze the hyperthermia potential of other materials such as ferrometallic and manganese alloys, as it expected to decrease the Curie temperature due to the mixing of other elements in crystalline matrix. So we need the high absorption rate and we need the high magnetic field. This is what we are looking for now. I will tell you why. Because what is a magnetic property? You know, in quantum electron systems you have a 3D layer in, and 3D layer should be half empty in order to have a high magnetic system. So you should, with some manipulation, to making this kind of atoms inside. Yeah, it is possible. It is really possible. It's unworkable, but it is really possible. So now we are thinking to use not only carbon nanotubes but graphene systems, which is a quantum channels. Graphene systems giving the possibility to make the quantum channels in. So what we need? High sensitivity. We need high sensitivity, everything. So we need to use small energy, and results should be visible, easy visible, I mean. Reflection should be high. So we need to use the materials which are very sensitive. And these kind of materials are now, fortunately, our colleagues developed and received Nobel Prize some 4 years ago. So it's possible now, and we have now the projects with the graphene systems, and I do hope that we will have with users projects, Professor Ben. Very high level, using the graphene systems, graphene something, and it should give us the possibility to receive the highest level results. I do hope that your students will develop also this kind of things. Thank you for this presentation. If you have a time, I will start the next one. Or.
Thank you very much. And yes, I want one question,
Yeah.
maybe two questions.
What?
Two questions.
Yes.
The first they use the nickel and the copper. There's carbon nanocapsules, right?
Yeah.
In the future, you want to change it to even iron or some manganese.
Yeah.
Why? That position of copper or nickel. How about the poles for our body? That means the heavy metals.
Yeah.
That means
yeah.
you change your another.
Yeah. We are looking for two directions. One direction is to have a sensitive material, very sensitive to magnetic field. This is the one direction. We are working on this. At the same time, we are thinking that they should be not damaging for the for body. Yeah. So we should make the balance in between two things. Balance. And because for fit we need some investigations. In which direction, in which range, in which temperature or which magnetic field it should be damaged, or it should be not good for the different part of the body. For example, medical doctors asked us, for example, if you have a bust cancer is different things. If you have a stomach cancer is different tasks. So medical doctors are coming and saying that we don't interested how it works, but we need this result, and don't damage this and so on. And we should go on this way. Why we need in our teams different specialists? I mean, for different areas. Because of it. Because when you ask me why they are different, I cannot answer. I am not a doctor. Yeah, I should trust you
Yeah.
that you are telling this.
That's one. Another question is, if you use this cancer, right?
Yeah.
As you see, how to realize which one is friend, which one is enemy. I mean, how to control this. It should be healthcare. Anyway, that's another story.
Yes.
Yeah.
Yes. You know that. Of course. It's not our work. It's work
yes.
of the. I mean, the hospitals.
Yeah.
Hospitals. What they are doing today without this, yeah? They are using the NRA, yeah, as an influence on magnetic field. They don't care if it's influenced by temperature or by magnetic field or something. They don't know exactly. But the answer was, it's good, NRA is good, yeah? Yeah.
It seems very cheap.
Yeah.
The cost is not cheap.
Yeah.
That's okay.
So, but we are trying to understand why it's good,
Okay.
why it's happening. Yeah.
The scientific research, right?
Yeah.
Yes.
And so when you understand why it's good, we will influence on this parameter. Yeah. And what we are doing in reality.
Okay. And one question, one more question. 那么，他的教授他院士他讲的是生命科学的一些讲。